All right, so let's get going. Welcome back to week 12, and we're going to be continuing our discussion of regression. All right, so let's discuss. So last week we took a brief look at some issues in regression, and today I want to make a much deeper dive into it. All right, so let's talk about some of the things that you saw on your homework assignments, and then we'll maybe the things we discussed last time will become a little bit clearer, perhaps. All right. Okay, let's get started. So one of the things we were trying to understand is this R squared concept in regression, right? And I'm sure you've all probably seen it before in a different class, but this is a chance to refresh ourselves, all right? So when you were playing with this homework assignment, you probably found a couple of scenarios where R squared was either very high or very low, all right? So let's try out a couple of them. One situation was if you do something like this, and you pretty much have everything lined up perfectly, almost perfectly, right? You're going to get an R squared pretty close to 1. If you're off by a little bit here and there, the R squared will start dropping in a bit. I don't know when. Here, there we go. But it's still pretty good. It's like 0.99, right? So you can see that when the R squared, when the points are very close to the regression line, the R squared is very high. All right. Conversely, it should come as no surprise to you that if we do something like this, right, where the points are, the regression line is there, but the points are very far from it, we're going to get an R squared that's very low. Okay, no surprise. Okay, pop quiz time. The first graph I showed you, the first figure I showed you, the line was quite steep and the points were very close to it, and the R squared was super high. But this one, the line is not very steep and the points are far from it. All right, and the R squared is super low. But I've changed two things. I've changed the slope of the line, and I also changed how far the points are from the line. So I'm kind of tricking you by changing two things and saying, look, R squared is low. What if I only changed one of those things? What if I made a line that was very steep, but the points were far from it? Would the R squared be very high or very low? What do you think? Or medium? Well, I can't cover it. I wish I could cover it. Let's try it out and see what happens. All right. So I'm going to create a situation where now the line's going to be like, steep, but the points are still going to be quite far from it. All right. The points are still quite far from it, right? You notice this time the R squared is not super small, it's healthy. All right. It's healthy, even though I'm trying to make it very small, but it's very difficult to make it super small. All right. So there's two things that is affecting R squared. One is how steep that line is, or how different from the mean it is, right? Because the mean line is like a baseline explanation. So, and also how far scattered the points are from it. Let me try one more. This time, I'm going to make the line really flat, but the points are going to be very close to the line. Do you think R squared is going to be very high or very low or in the middle? Very low? Very high? Anybody say very high? How many of you say very low? Don't worry, I'm not going to hold you to, I'm not going to Okay, anybody say in the middle? No in the middles. I can see you're struggling with the hat. Very high? Oh, brave man. Let's see. It's like, let's see. I'm going to make it quite flat. So from here, let's say to here, which is quite flat, but the points are going to be very close. I'm not going to make it exact, but very close. Ooh, look at that. R squared is 0.93. So really, in terms of what affects the line more, is it about the slope of the line? What affects R squared more? Is it the slope, or is it the dispersion of the points from the line? Which one ruins the R squared more? The dispersion of the points from the line, right? So some people have a misconception that, oh, if the slope is not healthy, my R squared is going to be low. No, this is not very far from the mean line. In fact, I've very faintly drawn the mean line here. Can you see that? This horizontal line here, this dotted horizontal line is the mean line. It's not very far from my regression line. And yet the R squared is tremendously high. It's above 0.9. Okay, it's a nearly perfect fit. All right. So there's two things going on for sure. There's the slope and also how close the points are to the line, the dispersion of the points around the line. I should say more accurately, the residuals, which is this is the amount that the regression line is wrong by. So that's the distance of the points from the regression line, the residuals. Those seem to have an oversized effect on how big the R squared is. All right. Okay, that's a first glimpse at R squared, and I think you kind of get the idea then that this is high R squared, this is low R squared, but you're also seeing that it's not this simple a story. All right. Um, okay, so let's move down. Let's take a deeper look at R squared and what's going on. Okay, what it means, how it's calculated, and I'm going to look at this a couple of different ways. I'm going to actually just load up a previous set of points I drew last night. Okay, and let's take a look at some things here. So I'm going to do a few things. I'm going to actually compute a regression on these points that I've drawn, the X and Y that I've drawn on those points. Okay. Now I can ask the regression object that I've gotten now. When I ran LM, it would return to me a regression object. Okay. I can ask this object, please tell me what are the fitted points. And by fitted points, I'm asking for each of these points, where does the regression line think it should be? So for example, this point here that I'm got my mouse pointer on, the regression line thinks that it should be somewhere up here, right? And it's wrong by a certain amount. This point here, the regression line thinks it should be down here somewhere, okay? And we can ask the regression object, where does R think the fitted value should be? And I can do this with a simple, by just capturing the regression object and asking it what are the fitted values, okay? And I'm going to call those fitted values Y hat. All right, so in the handout, I've kind of shown like the fitted value is called Y hat. It's got a little birthday hat on it, okay? The hat really says that this is an estimated value. It's an estimate, okay? The actual value is Y. We had X and Y. The actual value is Y, all right? And of course, the mean value of Y is down here. That's this horizontal line right here, okay? So fitted value, actual value, mean value. We can also ask R, now that you have this Y hat, these estimated values, can we just plot them? Like for each X value, plot its corresponding Y hat. All right, let's see it. So I'm going to do points, and you'll see on my figure now that the Y hats are actually drawn on the regression line. These are the fitted values. For every point of actual data, there's a corresponding Y hat down here. All right. Now I can do a couple of things. I'm going to draw several lines to show you like some differences. All right. So first of all, I'm going to draw a line segment from each actual point, like X and Y, to the Y hat. So I'm going to draw a line segment to show you the residuals or the error of the regression, right? So line segments from the actual points to the y-hats, all right? Make sense? So this is how wrong our regression is. This is how incorrect it is, if you will, okay? And so that's this distance from here, y-hat to y, all right? Let's do another line. Okay, I'm gonna also draw. I'm gonna draw a horizontal line for the mean of the y's. It's already there, but I'm gonna make it a little bit darker. Okay, so there's a dark line here. Now I'm gonna draw vertical lines from the y's to the means, from the actual points to the mean. All right. Now in a very faint gray color, I've drawn horizontal lines from the points to the mean of the points. All right. Why is this important? Why is that distance important? Because if I was to calculate the variance of y, it would basically be the difference, it's y minus y mean squared and summed divided by the degrees of freedom, right? So when I'm doing the variance, the total variance of y, it's looking at these distances, these gray, I have no idea what's going on here. Oh, no, that was a different line. It's looking at these gray distances, like this distance from the mean to the actual points. That is the distance that is squared and summed to compute the total variance of y. All right. So let me go down here and show you an example. So when I'm calculating the total variance of y, forget the regression, just the total variance of the y direction is the distance from each point to the mean. And if we square those differences, we get the sum squares. And if we, if we square and then sum up those differences, we get the sum squared total of y. If we divide it by degrees of freedom, which is n minus 1, we'll get the variance of y, the total variance of y, okay? But forget variance, let's talk about the variability for a moment. The variability is simply these gray distances from here to here, from here to here, from this point down to here, these distances squared and summed, okay? The error variance is these distances, these red distances I plotted earlier, from the point to the regression line, these residuals. If I squared them and summed them, I would get error variability. And if I divided by certain degrees of freedom, I would get an error variance. Okay? And then the last of all is some blue lines from where to where? Okay, and then I'm drawing some blue lines. It's very faint, but you have to bear with me here. From the regression line down to the mean. From the regression line down to the mean. Okay, so from the regression line or up to the mean in this case. All right. So there's three differences we can look at. One is the difference of the point from the regression line. And that distance, if you squared it and summed it, you would get the error variability, or SSE, sum squared error. If you took the distance from the regression line for each x value from the regression line to the mean, that distance squared and summed would be the regression variability. That's how different the regression line is from the mean. Okay? And if you took the original points and the distance all the way to the mean, that's the total variability. If you squared and summed those distances, that's the total variability. All right? So one thing you know that R squared is actually this regression variability divided by the total variability, which is really the dispersion explained by the regression line compared to the total dispersion of the data. That's how much is basically asking how much of the total variability is explained by the regression line. All right, that's what R squared is. And that's one intuition of what model fit is. It's telling you how much better an explanation is, how much of the total variability of the data can be explained by this regression line. Okay, The amount of the variability that's not explained by SSR is SSE. So that's the error variability. So another way of writing R squared is 1 minus the ratio of SSE over SST, because SSR plus SSE is SST. All right. So that's one view of what R squared is. It's really trying to explain, it's trying to look at the total variability of Y, which is looking at each Y value versus the mean value of Y squared and summed, and asking how much of that distance could be explained by the regression line. Okay, and that's your R squared. And that gives us gives us one type of model fit. All right, it's asking how well does the line fit the data? Well, we're asking how much of the variability of the Y direction is explained by this regression line alone. All right. We can do this mathematically as well. We can calculate the residuals or the sum square error as just the difference from the actual Y's to the fitted values on the regression line, Y hat. Okay, squared and then summed. So let me forget the visualization for a second, and let's compute SSE. All right. Ignore this little last value thing. This is just basically printing out the last thing I computed so that I can both assign it to SSE and also see the value down here. All right. So it's just a little gimmick to print out the last computation on screen. All right. But that's my SSE. Any questions on how we're computing that? It's a variability, which is basically, it's a measure of dispersion. But in this case, we're looking at the fitted values and how far they are from the actual values. That's our error variability. Okay. Our regression variability is the fitted values from the average value of Y, that distance squared and summed. And why are we comparing the fitted value to the average value? And one thing we discussed last time is the average value is something like just a stereotypical guess of what Y is. If we had no model in mind and someone said, hey, I have an X, what's the Y? If I really don't have any model in mind, my best guess will be the average value of Y. Okay? So we're just taking a very naive guess of Y, which is always this average value, and saying how different is our fitted values, the points on the regression line, how different is that from just this naive guess? Okay? And that distance squared and summed is our regression variability. And our total variability is the actual Y values, the distance from those from the mean values of Y, squared and summed. Now that is the classical definition of variability, of a variable. Like if we were not talking about regression, if I just gave you this column of Y values and I said, what's the variability of Y? Well, you know that it's going to be this formula. It's the variable minus its mean squared and summed. Remember, that's the classic definition of variability. So that's the total variability of Y, all right? And it just so happens that, the regression variability and the error variability add up to be our total variability. Okay. Notice again, I'm talking about variability as a measure of dispersion, not variance, because variances don't add up because they're divided by different degrees of freedom. So they will not add up to the total variance. Variabilities do add up. So we like that property of variability, or sum squared, square of sums. All right. So I hope this gives you one sense of what R squared is now, right? And why it's considered a model fit metric is because it's really looking at the total variability of Y and saying how much of that variability can be explained by the regression line, by the fitted values, all right? And again, the fitted values are these points on the regression line, which is the regression line's guess of where this point should be according to the model, all right? What was the R squared here? The R squared here is 0.72, and this is typically considered a good healthy R squared. Somebody in the class last week, I forget who it was, asked me what is a good R squared. Was it you, by the way, in the hat? What did you ask me last week? Don't remember. Maybe. Okay. I don't know who asked me. Gentleman sitting somewhere over there, I think. What is a healthy R squared? Well, what if I told you that 0.7 is a healthy R, is one possible definition of a healthy R squared above 0.7? Any idea why that might be? No? Well, let's take a look at the next slide and we'll come back and ask this question again. All right? So my hint here, so why is R squared greater than 0.7? Considered to be most, when R squared is bigger than 0.7, we can say the variance of Y is mostly explained by X. Why is that? And my unhelpful hint here is, well, what is R in R squared? Okay. But before I get into that, any questions about what we've just seen on this slide? Are you okay with this slide? Yeah? This is the model fit perspective of what is R squared. Let's look at another perspective of what is R squared, okay? Because we each have, like, when we see a problem, each of us often a different solution clicks for us, okay? So a different explanation often works for different people. So let's look at a different explanation of what R squared is. For some of you, it may be more confusing. For some of you, it might be actually more understandable. I don't know. Okay, let's see. All right. So I told you that we have actual values of Y and we have fitted values of Y, right? And if I go here and I look at points dollar Y, these are my actual values of Y that I plotted on that interactive regression plot, correct? And then I computed a Y hat earlier, which is the fitted values of Y, which is where the regression line thinks the Y value should be. Are you good so far? All right. Do you agree with me that each of these is a vector of points, is a vector of values, right? You agree with me? Each of these is a vector. Y is a vector, Y hat is a vector, correct? I feel like I'm doing a magic act and I have to convince you. I'm not tricking you. So each of these is a vector. Well, do you remember from what, one or two classes ago when we have two vectors and we want to ask how similar are these vectors? What's one measure of similarity? Cosine. What's another measure of similarity? Correlation. What correlation is just a mean-centered cosine. Remember that? Yeah? Good. I'm in the right class. Okay. Sometimes, yeah, I don't know, I go to the wrong class and do 3 hours and everyone looks confused. But no one says anything. So you agree. And so if we're really asking model fit, how well does our regression fit the actual reality? Wouldn't an easy way to answer that question, instead of like SSR over SST and all this nonsense, wouldn't just be ask, well, the actual values of Y and the fitted values of Y, how similar are they? Isn't that another way of measuring model fit? I think so. Let's try it out. Gil, you look confused. You know, you're with me? Okay. All right, so let's do it that way. So what we're going to do now is I'm going to simply ask for the correlation of Y and Y hat. I can do that, right? And that gives me another, that's not the R squared value. What was the R squared value? Anybody remember? Is regression, right? And how did I get that? If I just type regression, it should tell me, right? No, summary of regression. Okay, so let's do the summary. The R squared is here, right? 0.71. What I'm doing now is I'm saying, let's take the actual values and the Y hat values, and let's just compute their correlation. All right? So that's how correlated my actual values of Y are from the estimated values of Y, the fitted values of Y on the regression line. And that correlation is 0.84. Is that the same as my R squared? No. But this is a correlation, also known by the letter R. Huh. What if I just took this and squared it? Is that my R squared? That's R squared. That is another view of R squared, right? So I showed you the model fit the variability view. This is another perspective of it. Is R squared is simply what's the correlation between what my regression line is thinking the points of Y should be and the actual values of Y. That's, that value is my correlation squared, R squared, and there we have it. Fantastic. So that's another way of looking at R squared, and that's another way of computing R squared. Okay. Now you'll remember. Okay. Anyway. If there's two vectors, there should be. Yes. 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 You're thinking of a correlation matrix, but that's when you have many, many, many vectors and you want to compare them all to each other, then that'll produce a correlation matrix. I just have two vectors, it'll give me one value, right? That's like one cell in your correlation matrix, right? Okay, great, yes. So this is another view of R squared. Oh, and by the way, I can do this with cosine as well, because I just need my cosine formula, which I wrote by hand last time, because R does not come with a cosine function for two vectors. And what I can do is I can just take the mean-centered value of Y, that's this is the mean-centered vector of Y, the mean-centered vector of Y hat, take their cosine and square it, and that'll also give me the same thing as correlation squared. Okay, so whether I use cosine correlation, it comes to the same idea. So R squared, another way of looking at R squared is it's the similarity of your actual Y values and your fitted Y values. It's the correlation squared. Okay, and that makes quite a lot of intuitive sense as well, because we're just asking how good are we at recreating our Y values. And as you can see, regression is very obsessed by trying to recreate the Y values, because that's the outcome we're trying to explain with our regression model. Okay. Yeah, please. X and Y. Yes. Okay, so what if we had a multiple regression? Okay, what if we had many values of X, right? But here, which correlation am I squaring here? Is it between X and Y? Am I looking at the correlation of X and Y here? No. Y and Y hats. If I had many values of X, how many vectors of Y hat would I have? Still one. It would still work. Okay? It would still work. Crazy. And this brings me to a next point. Y hat really captures what all the different X's are saying about Y. The explanation of Y that all the different X variables are saying is captured by Y hat. All right? So when I actually take the correlation of Y and Y hat, what I'm actually doing is taking a multiple correlation of Y and all the X's. Because all the X's, they're explaining what Y hat should be, right? So the big letter R is really often called a multiple correlation, because it's telling you how Y is correlated with the combination of all the X's. That's why it's the big letter R, not the small letter r. All right? In a simple regression, we can use the small letter r for the correlation between X and Y. We can use the big letter R as a correlation between all the X's and Y. It's a multiple correlation. So R squared is often called a squared multiple correlation. SMC is another expression for R squared. All right. All right, cool. So this is so I hope we've kind of nailed R squared now from two different perspectives. One is you can look at all the variabilities and ask how is regression explaining how much of the variability of Y is the regression line explaining, the fitted values explaining. But another way of looking at R squared is really it's a correlation between our fitted values and our actual values squared, no matter how many X's you have. All right, great. So I hope that gives you both a statistical and a kind of geometric sense of what is R squared and why is it considered model fit. All right, wonderful. Okay, let's move on. Something I just want to kind of conceptually go over, we may see it in more detail later, is these regression coefficients, right? When we had just a simple regression, the slope of x on y, if you were to standardize x and y, this is a little bit of a magic trick, but if you were to standardize x and y, then the slope of x and y is really the correlation of x and y. Okay, if you standardized x and y. So when you standardize variables, the coefficients, instead of calling them b, we call them beta. Okay, that tells you this is the slope of a fully standardized solution. X's and y's are all standardized. Okay, so this is so your beta coefficients, your regression coefficients, your slopes in a simple regression would simply be the correlation of x and y, little r. Okay. However, that is not the story in multiple regression. In multiple regression, the slopes become quite a bit more complicated, and maybe we'll discuss it some other time what this expression means, but not today. All right, but just want to let you know that the regression coefficient is a bit more complicated, but it could be intuitively viewed as a kind of partial correlation between this x and y with the other x's excluded. Okay, it's not exactly the partial correlation, but it's something like a partial correlation. All right, but I won't go into too much detail about that today. All right, so but these are how slopes are computed. In a simple example of two x variables, the slope of x1 would be written like this. It's got the correlation of x1 and y in there. It's got the correlation of x2 and y in there. All right, and then it's kind of like partially standardized by the correlation of the two x's. All right. Now, the other thing I want to mention, the thing I want to explain, I want to mention a little bit more, is this estimate of this slope that we get is of course just one estimate that we've gotten from your sample, right? From your data sample, we've computed an estimate of this slope, or let's say this slope, all right? However, if somebody else was to collect a sample from the same population you were collecting from, they would probably get a slightly different estimate than you would, right? And if a whole lot of people were to collect a whole lot of samples from the same population, they would all get slightly different estimates of the slope, right? They wouldn't be exactly the same as yours. What would the distribution of these estimates be? Like one person estimates a slope, another person, 1,000 people estimate slopes. What would the distribution of these slopes be? Well, it turns out that the distribution, so for example, let's look at this regression formula right here. So this is from your CARS data set that you looked at in the homework, but I didn't ask you to do this, but I'm doing a very small regression here with just cylinders and displacements. Okay, I'm just looking at the number of cylinders and displacement. By the way, um, we're not all English speakers, and in fact, hardly any. I think nobody here is a native English speaker, probably, and we're not all car enthusiasts either. So what do these words mean exactly? Cylinders and displacements. Just in case you were wondering. So like in a car engine, you've got these pistons. These are called pistons, and they go up and down to. Yeah, thank you, Billy, for the. They go up and down as to compress the gas, ignite it, and then they go down again, right? So these are pistons, and they are housed, and they're in a hole, in a cylindrical hole, right? Each of them are in a cylindrical hole these holes are called cylinders, all right? So the number of cylinders in your engine is the number you're looking at in the data. It's telling you how many of these holes and pistons do you have in your engine block, all right? The more cylinders you have, the more powerful of an engine you have, because it can extract more force, all right? So that's cylinders. Is that okay? Cylinders are the holes in which the pistons are going to be firing into, all right? Displacement. So now two cars can have, let's say 4 cylinders. Like we have two cars, each of them has 4 cylinders in their engine. However, in one car, the cylinders are a little bit bigger than the other car. So that car will probably have, I guess, a little bit more power because it can burn more fuel with every pump. Okay. So the volume of all the cylinders combined is called the displacement. All right. So that's what displacement means. So cylinders tells you how many pistons and cylinders, and the displacement tells you, well, what's the volume of these cylinders combined? Okay, so that's, I just want to kind of get you a little comfortable with the terminology of this data set, since nobody asked, or maybe, I'm also afraid that in the coming years, as cars become electric, people will be like, what the hell is that? I've never seen one of these before. All right, okay. I have to soon find another data set for electric cars or something. I don't know what to do. Just retire before that happens. All right, so for cylinders, the slope was minus 0.51, which tells us, what does the slope mean? It means for every, so hold on, for every cylinder, how much does the miles per gallon change? So for every cylinder we add, our fuel efficiency, or miles per gallon, how far we can drive on a fixed amount of gas, our fuel efficiency drops by 0.51. Of course, you got a more powerful car, you're burning more gas, okay? So our fuel efficiency drops, okay? So that's what the estimate is telling us, right? Um, and this estimate, as I said, if we were to have a slightly different data set, we would have a slightly different coefficient. This coefficient is minus 0.51, which is about here, all right? And if we were to collect different samples of different cars, I mean, we just have a fixed number of cars here. If we were to pick slightly different cars, we might get slightly different coefficients. The distribution of these coefficients would, however, follow a fairly normal distribution. Okay, a fairly normal distribution. All right? And the dispersion of this distribution, so how different can the coefficient be from what we got? The estimated standard deviation of this distribution is given right here. It's called the standard error. So we're being told this is the estimated slope, but it has a standard deviation of 0.44. So it could be, 1.96 standard errors to the left or right. All right. So we can use this standard error times 1.96 positive and negative to either side of this estimate to get a confidence interval of this estimates. Okay. And in doing that, we can perform a t-test, and this is the t-value that they give you. All right. So here they basically compute a t-value using the estimate, and they ask how far is this estimate from zero. They divide it by, they do the whole t-test formula using the standard error as well. And this is the t-value they get, minus 1.169. And this is the corresponding p-value for a two-tailed distribution. All right. So basically, I drew this wrong. There should be two tails here. There should be two tails here. But it's basically telling us a t-test of whether null hypothesis is that the coefficient is zero. And the bigger our t-value is, the more confident we are that minus 0.51 is not zero or could not be zero. However, as you look at this p-value, zero is completely in the 95% confidence interval of this coefficient. All right. I'll come back to this at the end of the class if I have time, but I got to move forward. But I just want to let you know the coefficients you're getting, they're just estimates based on your sample. They have a distribution in nature, if you will. If other people sample, they would get slightly different coefficients. Overall, all the coefficients you could get should follow a fairly normal distribution. Okay. And we can use our regular, and we can actually estimate what is the standard error of the slope estimates. The formula for that is on the previous page, actually. The standard error for for coefficients can be actually computed from y and y hats. Okay. Oh, excuse me. That's the standard error of the regression. The standard error of the coefficients of a actual standard error of a coefficient is computed from the standard error of y, which is computed from as the standard deviation of y versus y hats, divided by this variability of that particular x value. Okay, so that gives you this. That's how the standard error is computed. All right. All right, let's move on. I'll come back to this later, but just want to let you know that our coefficients we get are just estimates. They have a distribution which has a standard error. We can do t-statistics on it. Moving on before I lose everybody. Let's take a look at the full regression model that you did for your homework. All right. So when you did the full regression problem, you got something like, let me close this one down. All right, let's go to, hold on. Clean up my workspace. All right, so let's do this. Let's load the car data set. Now you'll notice that the cars data set that I gave you, I believe, doesn't come with any names. Is that correct? Right? And I think I asked you in the homework, please go ahead and give some names to it. Did I give you a data set with names or without names? Without names. And I gave you this code to add the names to it, right? Okay, great. All right, so then we got the names. Now, many of you, as you should have, taken a look at the data first. Let's kind of view. Okay, so let me do this again. So view cars. So this is the original data set. It looks like that, right? As I add the names to it, the data set looks like this now, right? Anything interesting to note? Miles per gallon it's got a 0.0 value at the end, but actually it's rounded to the nearest integer. The cylinders are numbers like 4, 6, and 8. I don't think there's any other values in here. Is there? Oh, there's a 3. There's from 3 to 8 somewhere. These are the displacements, horsepower, weight, acceleration, power, how fast this car can accelerate. The model year, so these are fairly old cars in the 1970s. Okay, there are newer data sets you can look at as well. And this is the origin of the car. Does anybody remember what the origin is? 1 is US, and 2 is Europe, and 3 is, in this case, it was only Japan. It was the 1970s. Okay, they were like, Japan, they can't make cars. Then the 1980s happened and Japan killed them all. All right. And as many of you intuited, we can't really use this car name in our regression. All right. There could be something inventive you can do with it, but I did not ask you to do that. So what I'm doing is I'm going to simply remove this car name column, and I'm going to do it like this. I'm just going to tell the cars data set, look at the car names vector, and just kill it. And when I do that, it just kills that column. It's gone. All right. So I know there's other ways of doing it. This is one way of doing it. All right. Okay. And then I can run my what was this one? Okay, I did that one already. I can run my full regression model here. All right. I can run my full regression model here. And let's take a look. Let's take a look at the summary of results, which is here. All right, and I've also shown it up here. So this is the summary of results. Couple of things. Origin, the country of or the country or location where the cars were made. This is a categorical variable. 1, 2, 3. It doesn't mean that 3 is better than 2 is better than 1. Well, it might, but that's not the intention. It's just we have to categorize, is it from US, Europe, or Asia? So we made it 1, 2, or 3. It doesn't have any kind of ordinal meaning. All right, it's just a pure categorical variable. So we tell R that this is a factor, which in this case simply means that the value is not actually have a meaning. It's just a category. All right. And the last thing we do, and the other thing we do is we can tell it just exclude any rows with like missing values in them. All right. So we run our regression and our results look like this. So we get these estimates, standard errors, t-values, p-values. All right. As we said, we can interpret these estimates. So for cylinders in this case, notice that the estimate is a little bit different than the simpler model we looked at before. So instead of minus 0.51, it's minus 0.489. So for every cylinder we add, the miles per gallon goes down by 0.489. All right. So this is nice. However, one problem with this kind of raw regression can be each coefficient is quite interpretable, but it's often hard to compare the coefficients against each other. Okay. Like how would you compare the coefficient for cylinders versus the coefficient for, I don't know, horsepower or weight, right? Like for example, here the coefficient is 0, it's times 10 to the minus 3. So it's minus 0.006. It's a very small coefficient. Cylinders is minus 0.489. It's like 100 times bigger. Does that mean the number of cylinders you have is 100 times more important than the weight of the engine block or the car, whatever it is weighing? Probably not, but the coefficients don't tell you what the relative importance is between the different variables. So you cannot interpret coefficients like that, okay? By themselves, the coefficient gives you, in the raw units of the data, some explanation. If you do want to compare the coefficients to one another in some way, one possible solution is to standardize the whole data sets. All right. So if we run a standardized, so let me look at the code for how I'm standardizing it. There's many ways to standardize it. This is my way of doing it. Okay. I've told it that my data is this time coming from a scaled version of the car's data set. All right. So if I don't tell you where the variable is coming from, assume it's coming from a scaled data set. All right. So miles per gallon is now scaled. Cylinders is scaled. Displacement is scaled. All of these are now scaled. All right. Couple of possible issues. Model year is also scaled, which is a little weird, but okay, we'll go with it. But the origin of the cars, we don't want to scale this because 1, 2, and 3 doesn't have a meaning. You can't standardize this and get a meaning out of it. Okay. So here you'll notice for the origin, rather than letting it pull it from the scaled data set, I'm telling it, no, get it from the original cars data set. And it's a factor. So I'm telling it, don't scale the origin. It's of no value to scale it. It's a categorical variable. All right. So now these are our standardized results. All right. And this time, there can be some relative comparisons you can make, because what is the units of each of these coefficients now? How does it work? It says for every, so let's look at cylinders. For every cylinder? No. For every standard deviation change in cylinders, there is a minus 0.1 change in standard deviations of miles per gallon. All right. So we're now looking at just, so the units are all in standard deviations, or you can think of it as no units, but there are some units as standard deviations now of the original variables. All right. So how does that help us? Because each of these variables has a different dispersion, right? And this is kind of important to realize. If we take a look, for example, at, where are we? Like cylinders, our cylinders values, they go from 3 to 8, right? If we look at the car weight goes from 1,600 to 5,000. It has a considerably higher dispersion. So what we've done is we've just kind of scaled them all to have the same scale, roughly from -3 to 3. All right. So if we look at the histogram of cars dollar weight, originally the histogram looks like this. Now let's use let's scale cars weight, and let's can I just scale cars as data frame? Okay, and let's call this cars STD is equal to, okay. So now let's look at a histogram of the standardized cars. Does that work? Let's see. Yeah. All right. So actually, the figure is more or less, it should be exactly the same. The bins are slightly different, but the distribution should be the same. It's just that the scale has changed now to roughly -3 to 3. Okay. So we're just rescaling all the variables to have the same dispersion. All right. So now we can kind of do some comparisons. We can look at cylinders with its coefficients and standard deviations of -0.1, and we could look at weight with -0.72. Okay, the raw coefficient of weight was -0.006, but the standardized is 0.72, which tells us, given the natural differences in the number of cylinders or in the weight, it appears that the weight has a larger effect on miles per gallon. All right, when we take into account what its actual range of values could be. All right, so that was doing a standardized multiple regression. Any questions on this? All right, so the raw regression is great if you want to interpret a particular coefficient. The standardized regression might be a little bit better if you want to compare, if you want to compare two coefficients. We're going to get to that in the next slide. Yes, I saw this question coming. I stayed up until late night to answer your question. All right. Okay. All right. Okay, let's move on. Yeah, I think a lot of you had questions about this factor origin and why it appears twice in our coefficients, but not 3 times. There's 3 levels, but there's factor 2 and factor 3. Where the hell did factor 1 go? Okay. Well, let's talk about, was that going to be a question or something different? Okay, tell me then. Yeah, the R squared is the same. We're not explaining better or worse. We're just rescaling all the values. Okay, for interpretation. It would be like, like let's say you go to like a hospital in Taiwan and they say, hey, what's your weight? You tell them the weight in what units? Kilograms. But possibly if you go to, let's say, the United States, I forget what doctors use there, but they don't use kilograms, they use pounds. So you just rescale your weight, but your health doesn't change because you've got a different scale. Like, oh, I feel much better now. Yes, I shouldn't go back to Taiwan. No, it's just rescaling, right? So we're just rescaling. The explanation is still the same. Great. Thank you for that point. Very important points. Yeah. Okay. All right. Let's talk about these dummy variables for a moment. Okay, so last week we looked at this simple example of a dummy variable. We had a different data set where we were looking at programmers' salaries, remember that? And we were regressing it against how much experience does a programmer have? What was their score on some kind of entrance exam or exit exam from the university? And do they have a degree or do they not have a degree? So our dummy variable here was like, do they have a degree? Do they not have a degree? This is a categorical variable. We don't know which one is better. Who knows? Maybe there's no such thing as better. Everyone is different. Okay. However, if we want to consider put a categorical variable into our regression, then we have to codify it as 0 and 1 or some distinct integers. All right. And what we actually, I don't think I did it here because it's just 0 and 1, but ordinarily, I should say factor degree, all right? And we can interpret this coefficient as, again, the outcome is salary. So this coefficient is having a degree changes your salary by this amount versus not having a degree. The difference between 0 and 1, all right? So now what do we do with car's origin? Because if I plot the origin of the car, that variable, against miles per gallon, well, miles per gallon is kind of a continuous variable, but you see there's only 3 types of origin, 1, 2, and 3. And the plot looks something like this, all right? When you plot cars, the origin of the cars versus the miles per gallon. And when I run the regression, I'm telling it factor origin. So I'm going to do a very simple regression here where I simply take the origin of the, so I just plot it like this. And then if I run a regression of just the miles per gallon regressed over only the origin, okay, only the origin, just to make our explanation a little simpler. So we get 2 coefficients, one for factor origin 2, one for factor origin 3. That kind of makes sense because we have origins 1, 2, and 3, but where did origin 1 go? Why is this not in the regression? It's so Stephanie's explanation is that these estimates are already considering origin 1. How? And let me go back quickly to the programmer example with a degree. This, remember, we had 2 levels of degree, 0 and 1, right? How many coefficients do we have? 1. It's telling us the difference of degree 1 versus degree 0, right? Now, in this example, we have 3 origins, 1, 2, 3. This coefficient is telling us, what is it telling us? It's telling us what is the difference in miles per gallon if you changed from factor origin 1 to factor origin 2. Is using factor origin 1 as a baseline. And it's telling you the difference between 1 and 2. Between European cars, one is what? One was US cars. Okay, so it's telling us if we have a European car versus a US car, then your miles per gallon goes up. You have a more fuel efficient car. In the 1970s, I don't know about today, probably the same. Okay. All right. So it's just telling us European cars are more fuel efficient than American cars. I don't think Americans ever cared about fuel efficiency. They're like, we're not even interested in that. All right. What is this one telling us? Factor origin 3. This is telling us having a Japanese car gives you this much more fuel efficiency than having an American car. So basically what the LM function in R is doing is if you give it a categorical variable, it's taking the first level it finds, like the lowest level it finds, and using that as a baseline. And then for the other categories, it's telling you how that's different from the baseline. All right? So that's why you're seeing two slopes instead of three. Because what would the third slope even be? US cars instead of what? No car? Like there's no comparison you could make. With three categories, there's two comparisons you can make. Well, you could make a third comparison, which is Asian versus European, but that would have no more explanation than what you're doing here. Okay? It has no further explanation than what you're doing here. So that's a redundant explanation. All right? It just picks one baseline, compares everyone to that baseline. And you can infer in between. So now if you want to know, yeah, Billy. What if you want to change the baseline? Good question. I don't know the answer to that question. The stupid way to do it would be maybe recode the dummy variable so that, let's say your baseline was going to be European cars. So you would make one into European cars and two into American cars. There might be another way of doing it, but I'm not sure what it is. So when you ask me a question I don't know the answer to, I have a punishment, which is you need to Google it and tell us now. Okay? Shows you right, huh? Dare ask me questions I don't know. I should have pre-approved questions you can ask, and then cannot ask anything else. I'm very curious to know the answer to that question as well. So, all right. Any questions about this? Are we okay with categorical variables? All right. Cool. Moving on. What are we moving on to? Oh, you had another question. I didn't know that. Sorry. Go ahead. Oh. Right. You know, I would think it wouldn't make a difference. Let's try it. I'm going to scale the origin. Okay. Well, first, these are the results of the raw regression with factor origin only. Okay. Let's run this again with the scaled origin. My guess, and I have never done this before, so should I pause the video? No, I'm kidding. Should like censor this part. My guess is it won't make any difference. Why? I'm going to scale it, and sure, scaling cars dollar origin, changes the numbers, right? From 1 to 3, we now get this ridiculous thing, right? But you notice we're still only getting 3 different values. Of course, we're just rescaling it. So my guess is if I was to do this, but I was to scale, I'm going to scale just the origin here, not miles per gallons, just to see if scaling this variable makes any sense. My guess is it won't make a difference because R will simply say, this is a factor. Well, I see 3 levels. Let's do it again. All right. So I think when you do this, does it make a difference? Nope. My estimates, 27 and 10, is the same. okay? Because R simply says, okay, now your origin value is just ridiculous, but that's what you wanted. Here you go. So I don't think it's going to make really much difference at all, right? You're going to get the exact same results. So yeah, it doesn't make sense. It just makes your output uglier. All right. Okay. Start the recording again. Okay, got it. Okay, great. Moving on. Now can I move on? Moving on. So regression comes with a certain, to be able to accurately interpret regression. Okay, regression will work like a lot of statistics works, whatever data you throw at it. Okay, almost whatever data, like all kinds of data will work on it. All right, but if you can, but the question is, can you actually interpret what comes out? All right, so for example, in this case, we are trying to interpret what does this coefficient, what does this coefficient mean, right? And we're interpreting it, every coefficient, we're interpreting it, assuming that that coefficient will, if you resampled, follow some kind of normalish distribution, okay? Which has a standard deviation of about that much, which we call the standard error, all right? And then we can, like, interpret its p-values and t-values, assuming those p-values and t-values actually follow a t-distribution. That the t-values actually follow a t-distribution, okay? But for our interpretation to be correct, for the coefficient to actually have a fairly normalish distribution, for the t-values to have actually a t-shaped distribution, there are some assumptions that we have to hold true, like some conditions have to be met, okay? Otherwise, you're not going to get perfect distributions, and your interpretations could be a little bit off, all right? What are those assumptions? And so there's three classical assumptions of regression, all right? And some of them, and you kind of have to, the way they're defined may not give you a good understanding of what to look for. So I'm kind of telling you what the requirements are for regression on the left-hand side here, and what it implies for your data on the right-hand side here to a certain degree, okay? So one of the, so the implication, okay, so the requirements are that once I've done a regression, and I'm showing you here kind of like a 3D version of a 2D regression. And let me try to explain to you what I'm showing you here. So you see the x-axis and the y-axis here. So I've basically taken x and y, and I've kind of like dropped it down on a piece of paper, and so you can pretend you're seeing it on a sheet of paper. All right, and the paper is on the table, and you're at a bit of an angle. So this is our x-axis here, and this is our y-axis here. And you see the scatter of the data points. These are the points of data here, right? Okay. And our regression line is this thick blue line running through the points. Are you okay with that? I'm showing it to you at this weird angle because I want to show you something at a different angle, which is if we ask for any given value of x, so let's say x is 10, 20, 30, what is the variance of the y values at that point? And you notice in this data set, the dispersion of the residuals, actually, the distance of each point to the regression line, um, the residuals kind of follow a normal distribution, whether x is 10, x is 20, or x is 30. Do you see that? Is this perspective drawing working on you? Yes, it is? Good. So it's kind of like a 3D picture, if you will, okay? Where I'm trying to show you the density plot of the residuals. Does that make sense? Because I'm basically looking at the distance from the regression line to the data points in the y direction, okay? And I'm showing you the density plot of the residuals, and they all kind of follow a normal distribution. Regression assumes your residuals follow a fairly normal distribution. They assume the residuals should be centered around the regression line. okay? And that it's a random normal distribution. There are some cases where this could be violated. For example, in this data set, if you can just for a second ignore the distributions, if you look at the data points, do you notice they kind of follow like a funnel shape? Like they're very close to the regression line here, and they start getting further as x increases. And then as x becomes much bigger, the data points, the residuals are much bigger, right? If this were the case, we're going to have trouble interpreting our results because we're violating one of the assumptions of regression, which is, and this is the second one here, the variance of the residuals should be the same for all values of x. But in this picture here, as x increases, the dispersion of the residuals also increases. It changes by the values of x. Now, you can still run the regression, you're going to get results, but all those standard errors, t-values, p-values, they will not be correct. All right? To be able to actually interpret the values that you're seeing in like these regressions, we have to have these assumptions that our residuals are, fairly normally distributed around the regression line. And if it's not, your interpretations of the regression will be off. So let's look at some situations where possibly these assumptions are violated. And it may help you understand these assumptions a little bit better. Okay? Okay. So one of the things I asked you to do was to try to visualize this data set. And there was a couple of really interesting differences in how people visualized it, and I really appreciated seeing it. The one I used, which I saw a lot of students used as well, was to simply, yes. You can actually ask R, just plot all the just all the variables, all right? And it actually gives you a fairly pleasing picture like this, all right? And this is like showing you scatter plots, and these are bivariate scatter plots. It's showing you, for example, this picture up here is the scatter plot for cylinders versus miles per gallon. Okay. This scatter plot over here, and symmetrically this one up here, is the scatter plot for miles per gallon versus displacements. Okay. Now, what's the difference between these two? The way R shows it, let's take this one. Horsepower and miles per gallon, its scatter plot is here. Since miles per gallon is coming in from the left, it is actually the y-axis here. And since horsepower is coming in from the bottom, it's actually the x-axis here. So this plot right here, it's horsepower on x-axis, miles per gallon on y-axis. It's going to be a teensy bit, it's going to look a little bit different than the corresponding plot down here. It's going to look a little bit different because here, horsepower is on the y-axis and miles per gallon is on the x-axis. Okay, so I would personally interpret the top right pictures where miles per gallon is on the y-axis because that's how our regressions are going to look as well. Okay. As you look at these pictures, you're going to notice some problems, some weird things. For example, if I look at, let's say, weight and miles per gallon, where am I in my plots here? Okay. Hold on, I'm going to define some colors here. Where is weights and miles per gallon? I thought I did it here somewhere. Weights. Huh? Okay. I think I just have to write the code. It's right here. Excuse me a second, okay? Oh, it's right here. Okay, it's right here. So this is just a plot, a scatter plot of weights and miles per gallon. And you notice it's a little weird to talk about the slope of this scatter plot because the relationship is not linear. Like the scatter plot kind of looks like a banana. This is like a banana shape, all right? Because it kind of curves this way. So if we draw just like a line through this, it doesn't exactly make sense, all right? It wouldn't exactly make sense because the relationship isn't linear. And regression is trying to create linear relationships with slopes. And actually, a lot of these have this same problem. Miles per gallon has this problem with displacement, with horsepower, with weight, with acceleration. All right, all these relationships are not linear. They all have this kind of banana shape, or this has a, what the hell is this? Eggplant? I don't know. Depends what kind of eggplant. Okay, but it's got kind of weird shapes to it. So these coefficients we're looking at is just trying to draw a line through these, and that doesn't make sense. All right. So we have a non-linearity problem in our data, where regression is trying to find linear relationships in non-linear data. Oops. All right. There's some other problems, and I don't know how many of you caught this one. Let's look at the picture of displacement and miles per gallon. So let's do this again, but I'm going to do displacements. Okay. First of all, we have the problem we discussed before, whether if you draw a regression line through this, the residuals will have greater variance as you go further along weight. There's a term for this situation. So it's like this picture here. It's called heteroscedasticity. All right. And that's one problem, but there's a more serious problem. Anybody know what the more serious problem here is? It looks like steps, okay, but I think regression can handle that. What is this relationship? Is this a positive correlation or a negative correlation? A positive correlation? It's a positive correlation, right? As weight goes up, the miles per gallon goes up, which means our fuel efficiency is getting miles per gallon. No, it means, oh wait, hold on. Hold on. I've displayed the wrong thing. It should be, sorry, I'm doing this all wrong. Displacement MPG. Look at completely the wrong variables. Sorry. There we go. There we go. Banana shape. Um, this is a negative correlation. Sorry. This is a negative correlation. Okay. This is a negative correlation. So as the displacement goes up, our fuel efficiency drops. Okay. Phew. Thank God. All right. Now, yes, this is a nonlinearity problem, but there's one more problem. This is a negative correlation. However, do you remember when we actually ran the regression? What was the coefficient of displacement versus miles per gallon? It was a positive slope. What? This is telling us as displacement goes up, miles per gallon goes up. But the visualization tells us the opposite story. It tells us as displacement goes up, miles per gallon goes down. It's a negative relationship. Which one should we believe, our eyes or regression? The regression, how many say, okay, how many of you say you should believe your eyes? How many of you say you should believe the regression? Okay, just checking, checking. Well, it would be a little hard to actually argue against this visualization because literally, if I buy a car out here, I'm going to get lower fuel efficiency than I buy almost any car back here. It's a little hard to argue against the reality of this. So why is regression telling us the completely opposite story? It's telling us it's a positive. We'll come to that in a moment. Okay? So there's a couple of problems we've identified already. Nonlinearity and completely flipped relationships than what reality is telling us, what the visualization is telling us. Any other problems in this data set? By the way, I love this data set because it has so many problems. Okay, that's why we use the data set. Not because it's so perfect, it's because it's so imperfect. And actually, data sets are imperfect. That's why we want to use this. All right? Any other problems? Well, let's take a look at some residuals. So let's run some, let's see. So remember I did this regression, this full regression earlier, right? RGR, and that was this full regression, summary. And that's this full regression of all our variables trying to estimate miles per gallon, right? The residuals, and we cannot really visualize the residuals of the full regression because the full regression has one dependent variable, it has one y variable, and how many x variables does it have? 1, 2, 3, 4, 5, 6, and actually 7, 8. This scatter plot is in 9 dimensions, 8 directions of x and 1 direction of y. We cannot visualize this. We cannot even imagine it. It's beyond our human imagination to visualize 9-dimensional data. We could possibly do 3-dimensional. 2-dimensional is easy. 3-dimensional, a little bit tricky. Beyond that, bah, it's in our imagination. It's in math. Okay? But this is a 9-dimensional, so we can't visualize it. However, the residuals is literally the distance from each point in this 9-dimensional space to the regression object. Okay? And by the way, the regression object is an 8-dimensional object, right? Because if you have 2-dimensional regression, you have a 1-dimensional regression object. If you have 3-dimensional regression, your regression object is a plane, which is a 2-dimensional object, right? In fact, your regression object is in as many dimensions as there are x variables. So a regression object is an 8-dimensional object. I have no idea what the hell that even is, okay? However, the distance of each point from 9 dimensions to the 8-dimensional regression object is just a 1-dimensional distance, all right? So the distance is pretty easy to get. The residuals are pretty easy to get. And in fact, the regression we ran, it will actually, just like we can get fitted values, we can get fitted values in 9 dimensions because the fitted values are just in 1 dimension. They're a distance from the, no, excuse me. They are just they're just y values. They're in 1 dimension, okay? The residuals are a distance from each point to the regression object, and it'll also be it'll just be a distance, so it'll be just like a distance which is 1-dimensional, okay, from each point to the regression object, all right? And so these are the residuals of our regression, and we can plot the density. Well, I've got the code here. We can actually plot the density of these residuals, and you'll see that our residuals have a more or less normal-ish distribution, but it's a little bit skewed to the right. That's this black distribution here, okay? However, if we were to do some smaller regressions, for example, this is a regression of miles per gallon just on cylinders, or miles per gallon just on horsepower, miles per gallon just over acceleration. If we do some simple regressions like these, all right, we will notice that the residuals of those simpler regressions do not follow a normal distribution, and they're skewed. All right? These are the density plots of those other residuals. So there is a problem that's this picture right here, there is a problem with our residuals. They are not distributed normally around the regression with, when you do miles per gallon over those variables, right? So we have at least 3 different problems in our data sets. Nonlinearity, completely opposite effects from what the regression is telling us, and residuals, at least if you do bivariate regressions, they're not normally distributed. They're skewed. The residuals are skewed, okay? And the problem with the residuals being skewed is that these standard errors assume that your estimate follows a kind of a normalish distribution, right? And it's telling you the standard deviation of a fairly normal distribution. But if it's skewed, well, it means nothing then. All right? So these are several problems that we have with our regression. And in fact, if we were to interpret and make business decisions based on this regression, we would be in terrible problems, because we would be saying such things as, hey, we better increase the displacement of our engines to improve the miles per gallon, the fuel efficiency. Bzz, completely the opposite. All right? We would be coming up with estimates and saying, oh, if we dropped our or increased our horsepower, this is how much we estimate the miles per gallon will drop. Wrong, because it's not a linear relationship, it's a nonlinear relationship. If we were to make decisions on what is significant and not significant based on standard errors, we would be wrong because the residuals are not even normally distributed. Every single decision we made on this set of results would be wrong. And let this be a warning to you that when you do statistics, unfortunately, in a lot of classes, in a lot of applied statistics classes, not in a real stats department probably, a lot of our effort goes into just interpreting this table. But if you don't set your regression up correctly, one or more, or in this case, all your interpretations are going to be wrong. All right? And in this case, there's not a single interpretation, not a single coefficient or t-test that is dependable here. They're all wrong in different ways and for different reasons. So I want to spend the rest of this lecture to talk about what's wrong and why they're all wrong, and try to find ways to possibly correct them to some degree. Okay? But before we get into that, let's take a little break. Okay? We'll come back, be charged, refreshed, and we'll fight this regression problem and get it under control. All right? Okay, let's take a little break. It's 10:34 right now. Let's start at no later than 10:45, which means in 8 minutes, you need to start making your way back into this room. And at 10:45, that door's going to close, and I'm going to start teaching again. All right? All right. Let's take a break.